Good day everyone, I'm Christopher Martinez presenting the study entitled Inflow Simulation and Load Computation using CFD of the Siargao Gymnasium with the help of my research advisor, Assistant Professor Dr. C. Agar and Dr. Heimer Hernandez. This will be the overview of my presentation. To provide a brief background, Siargao Sports Complex Gymnasium is one of the facilities built in the Siargao del Norte under the DPWH program in January 2020. A year after its construction, Siargao Island was devastated by Super Typhoon Odette with peak winds of 193 kph. Due to the onslaught of the Super Typhoon, the gymnasium experienced structural failure of the roofing system, wherein the roofing system exhibits an arc roof shape and specified on the NSCP 2015. However, the corresponding design wind load of Siargao del Norte may not be anticipated in the design of the roof shape. With this, the objective of the study is to determine and characterize the wind loads experienced by the roofing system by performing the following methods. First is the simulation of wind flow through CFD analysis using open foam. Next is to compare the code-based wind pressure coefficients from the results of the CFD analysis. And lastly is to determine the wind load experienced by the roof fasteners of the Siargao Gymnasium. Here are the significance of the study, in which it will be significant in generating wind flow simulation model for risk and damage assessment of arc roof shape structure. It will also provide design recommendations for arc-shaped roofing system, and lastly establish code-based wind load provisions using wind flow simulation. The scope are the following. The modeling of the gymnasium will be based on the approved structural plan of the gymnasium. Wind flow simulation will be conducted in open foam software and be validated using TPU wind tunnel database. Third, it will only cover arc roof shape of the gymnasium, in which structural analysis will not be conducted in the study, and lastly, only the onset of the roof failure will be considered. This is the general overview of the methodology, starting on the modeling of the gymnasium using ANSYS, followed by the validation procedure based on the TPU wind tunnel database, then CFD analysis using open foam, wherein the results will be compared to the wind load provisions of NSCP 2015. From the CFD analysis, wind pressure coefficients will be obtained and can be converted to the wind loads acting on the roof fasteners, and lastly to determine the possible locations for the onset of the roof cover failure. Specifically, the CFD analysis has three distinct methods: the pre-processing solver and the post-processing. For the pre-processing, it involves the modeling of the gymnasium using ANSYS, in which three cases were considered. First is the enclosed structure and partially enclosed, considering two cases of the onset of failure based on the actual video footage of the roof failure. Next is the computational domain boundaries used in the wind flow simulation. Next is the mesh generation using open foam. Presented are the dimensions and cell sizes for the outer region or the coarser region, and the cell sizes for the finer region or the mesh for the building envelope. After the mesh generation and modeling, validation procedure was conducted to determine and to validate the initial boundary conditions for the wind flow simulation. The objective is to replicate the results of the TPU wind tunnel database for wind incidence angle of 0 degrees, 23 degrees, 45 degrees, 68, and 90 degrees. After validation, the locations of the probe and roof fasteners were determined based on the location of trusses and purlins based on the structural plans of the gymnasium. For the wind speed, two values were considered based on the Siargao City Station and the calculated wind speed on the Siargao Island, including the wind incidence angle of 50 degrees. With that parameters and boundary conditions, simulations were conducted with wind incidence angle of 0, 30, 60, and 90 degrees, considering the wind speed of 58 meters per second. Similarly, three simulations were run for the three cases for the enclosed and partially enclosed structure, considering the actual wind incidence angle of 50 degrees and actual wind speed of 90.705 meters per second. From that, here is a summary of the CP values obtained from all the simulations, considering different wind incidence angle. Presented are the minimum, maximum, and mean roof wind pressure coefficients, in which the actual wind incidence angle is marked by the red dashed line. Similarly, the coefficient wind pressure obtained from the CFD analysis were compared to the NSCP code-based provisions, specifically for wind directed or perpendicular and parallel to the axis of the arc. The percent difference were also calculated. From the CP values obtained from the wind flow simulation, it is converted on the wind load experienced by the roof fasteners in which negative wind loads were experienced, indicating uplift forces on the roof fasteners. So the following locations and the magnitude of the negative wind loads were presented in a slide, including the wind flow parameters. Similarly, the maximum negative wind load for all the cases and for all wind incidents were considered. Presenting are the magnitude and the corresponding wind flow parameters, in which the maximum negative wind load was experienced on the 30 degrees with wind speed of 58 meters per second. Based on the locations of the results, it corresponds with the locations of the on the actual onset of the roofing failure, as seen on the video footage. Lastly, the effects of the internal wind pressure coefficients were determined in which the external was subtracted from the internal wind pressure coefficients to determine if there is an increase in the number of roof fasteners with negative wind loads. Based on the results of the study, the wind flow simulation was able to record negative wind loads, providing the possible location of failure similar to the actual onset of failure of the roofing system of the gymnasium. There is high percent difference on the wind pressure coefficient between the results of the CFD analysis and NLCQ 2015, specifically on the windward region for the wind-directed perpendicular and leeward region for the wind-directed parallel. There is also a percentage increase on the roof fasteners experiencing negative wind load, considering the net wind pressure coefficient specifically for the case 2 of the onset of failure. And lastly, the maximum negative wind load is observed in the wind at incidence angle of 30 degrees at 58 meters per second wind speed. With this, the recommendations of the study is to analyze the progressive failure to validate the results obtained from the onset of the failure. Next is to conduct wind flow simulation using the actual wind speed with varying wind incidence angle, and to conduct structural analysis to determine the capacity of roof fasteners and determine the locations of failure leading to the progressive failure of the roofing system. And lastly is to determine the average wind pressure coefficient based on the tributary area of the roof fasteners. Here are the references.